Hello, this is Philip Myers of PEMY Consulting. Today I want to talk to you about the average uplifting pressure on both dome roof tanks and cone roof tanks. To get an understanding of this requires lots of computations based on ASCE 7-16, which we've done. These calculations will help us move forward in improving API 650, both its clarity and the methodology for computing wind pressures on roofs. Keep in mind that the plots that we'll see are all based on the wind velocity of 120 miles an hour, exposure C, and an ASD load factor of 0.6, which is incorporated into the plots. The tanks are, of course, 48 feet tall, and other factors are applied as you would expect. Before I show you the surface plots for wind pressure, I want to give you an understanding of what the input parameters are. For a surface plot, of course, there are two axes. One of them is the diameter. The other is F over D, the ratio of the height of the dome or the cone to the diameter. I just want to point out a few things about F over D so that when you see the surface plots, you'll have a good understanding of what's going on. Here we have F over D. For cones, at the minimum slope is 3/4 and 12, and that has about a 3.5 degree slope. The F over D is 0.031. A 2 and 12 slope, which is not uncommon, but which is probably the steepest typical slope for large tanks, has 0.083 for its F over D value. That corresponds to about 10 degrees. The domes, of course, are much steeper. Its F over D typically ranges from 0.11 to 0.21. So these gray lines show the F over D ratio for domes. This is the first surface plot for cone roof tanks. The two input axes are as follows. The first one is for the slope of the cone. 0 would be flat. 3/4 and 12 would be about 0.03. A 10 degree roof would be about 0.8, or right here at around the 0.1 mark. And then a 30% slope corresponds to about a 20 degree cone. So steeper is going to the left. On the other input axis, we have diameter ranging from small to large. Notice this shelf here. Large cone roof tanks, which are represented by about 200 foot and larger, and with shallow cones, a typical 3/4 and 12 would lay on this plane at a fairly low pressure of about 16 psf. Notice though that when the diameter gets smaller, below 200 feet, the average pressure of the roof starts rising rapidly. When the slope is more than 10 degrees, there's a sudden rise in the pressure. Steep cones, in other words, have a higher pressure than do shallow cones. That would be kind of expected from the intuitive understanding of an airfoil. So steep cone roofs have high pressures. They're in the order of maybe 19 to 21 psf. It's somewhat peculiar, but this is the result of the computational methodologies given in ASCE 716. This is the surface plot for a steel dome or geodesic dome. The F over D axis is down here flat up to 0.3. Geodesic domes live in the range from about 0.1 to 0.2, so this surface plot goes beyond the ranges that are actually used in the industry. On this axis there's the 50 foot to 350 foot diameter. So as a dome gets smaller, or more curved, higher F over D in other words, the pressure goes up quite high actually to above 25 psf. Alright, this is a surface plot for both domes and cones. The coral colored region is for cones, and recall that cones pretty much span the F over D from very shallow up to very steep. Most large tanks live down in this lower region. Domes, on the other hand, at a F over D of 0.1, about 10 degrees and larger, they are living on this upper region here. So what becomes apparent is that for large tanks, the cone roof pressure is greater than it is for domes. But when you get to smaller diameters in about 200 feet, the dome roof pressure is higher than cones. I can spin this around and look at what the cone roof pressures there would be. They flatten out at less than 20 psf, even for the steep cones. Okay, the surface plots can be represented here all together. This group of lines is for shallow cone roofs. Notice that they decrease and then flatten out. Steep cone roofs move upward because the average roof height is increasing, and as you recall, the exposure coefficient increases with elevation. Geodesic domes and steel roofs cluster in this group of lines. Finally, putting it all together and simplifying, these lines show the proposed rules for average pressures acting upwards on tanks. The blue line is for shallow cone roofs under 10 degrees. The formula is simple. Its pressure as a function of diameter is 0.031 minus 20.6 for diameters less than 150 feet, and then just a minus 16 psf for diameters that are greater. Cone roofs greater than 10 degrees, we have the pressure is negative 0.01 minus times D minus 18.42. We don't carry this out beyond 100 feet because it would be unusual and rare to find cone roofs that are steep at diameters greater than 100 feet. And finally, for domes, we have 0.03 D minus 25.5. This is the goose that laid the golden egg. I call it a golden egg because this work would never have gotten as far as it has without Bana Mistry and Randy Cassell, their initial work on framing this very complex problem. So it truly is a golden egg for the committee so that we can move forward and adopt the latest thinking in ASCE 7 wind loading. Thank you.